Our next talk is going to be by Hannah Topal and Javier Fernandez-Marques. Let me first introduce Tanner. Tanner is one of the creators of Flower. He is also a visiting researcher at the University of Cambridge. Alongside that, he is an experienced systems engineer and one of the founders of a startup in Hamburg, like Daniel, of course, it's ADAP. So he's going to be speaking alongside Javier. Javier is a PhD student, nearly at the end of his studies. He studies at the University of Oxford, and he has been working for the past number of years on areas of efficient ML on constrained devices. And the pair of them are going to talk to us about how you can use Flower to scale up the number of clients you use in analyzing your algorithms and understanding how your algorithm might behave in production or under a proof of concept. And so they're going to be speaking to us now with a talk called Scaling Up Federated Learning with Flower. So again, thank you, Virginia. And let's hand over to Javier and Tanner.
Okay, thank you, Nick. Can everyone see my slides?
Yes, we can see.
Yeah, yes. Okay, perfect. So first, So by now we have covered a few talks, and some of them we have learned more about Flower. And Flower, as a quick summary, is like a very versatile framework that allows you to do federated learning regardless on what machine learning framework you are using, whether it is PyTorch, TensorFlow, or MXNet, or even if you are not trying to use federated learning with neural networks, you want something more maybe traditional machine learning approach, you can even use NumPy for this purpose. This framework is as well client agnostic, meaning that you can use Flower to run your clients on for example, on a smartphone using TensorFlow Lite, or inside a Docker container in Raspberry Pis or Jetson Nanos. And as well, you can run this in a virtualized setting, for example, in a dedicated server or in your laptop. And over the last few months, we have seen a number of applications making use of Flower for quite interesting and different type of research. For example, analyzing what's the impact on carbon emissions of federated learning settings and how that compares to traditional centralized training in the data center. We have seen also how federated learning is used for speech recognition systems where there are very strong privacy concerns in those domains. And we'll see very soon also how Flower has been used to adapt a global model in a hardware-aware fashion. So given a maybe potentially computationally expensive model, how can we allow the training of that model regardless of how constrained your device is? And all this has been really amazing pieces of work from different members of the community. And what Tanner and I we have been looking at in the last couple of months is, okay, what extra steps do we need to give inside the Flower framework to support the next wave of papers and applications? And everything our discussions revolved around the idea of, okay, how can we set what are the resources for each client? For example, we have a number of clients, for example, for Shakespeare, as Virginia was mentioning, or Feminist. Ideally, we would like to set in a very easy to use manner how many resources we want for this client. For example, 1 CPU core per client and maybe 1 GB of VRAM. So currently that's not possible to do within Flower. So that's something we would like to introduce. In that way, because normally we have multiple clients per round, we could ensure certain isolation, at least in terms of compute resources and memory resources between clients. And in this way, the user doesn't have to really deal with, okay, how can I partition my 10 or 32 gigabytes of VRAM that my GPU has? How can I partition it in a simple way across multiple clients that are participating in a round? For example, another thing we have been hearing about in the previous keynote is clients are different. Some clients might need maybe more CPU others might need more GPU or not GPU at all. So how can we, within the framework, before we launch our experiment, how can we define this so it happens in a transparent way for us? Going even further, what happens if we want to launch, we want to use many more clients in a round that we can possibly fit in our device. For example, using my laptop, which is a 5-year-old laptop, how could I run 1,000 clients per round? So we have been thinking about these ideas, and one of the simple approaches, although it's not trivial to implement, is can we implement some type of scheduling? So within a round, we can have many models participate in this round, regardless of the resources we have in our system. How can we maximize resource utilization given our hardware? So whenever I have my experiment, I want to run it a different type of hardware. I don't need to worry about whether I'm using all the resources or not. As long as you have set the resources that each client needs, then can we design a scheduling mechanism that will run all those clients in a round, utilizing all the possible resources, meaning that our experiment will run much faster. What happens if we have now multiple GPUs? Can we scale to that in an easy to use manner? Or what if we have multiple nodes? Can we launch our federated learning simulation experiment just with a couple of commands? That, for example, will allow us to simulate also networking issues like stragglers or basically devices going down. So the idea is, okay, all these really exciting new techniques, how can we add them to Flower? And for that purpose, we envision a new type of client manager that we call virtual client manager. And the idea is that this virtual client manager will help us to produce the next wave of research. One of the key differences with existing client manager is that this client manager communicates with the server, but lives in the client side, meaning that if you have, for example, 2 nodes, one where the server lives and the other one where the clients live, the virtual client manager will live in this other node. And what this virtual client manager will do is it will spawn or launch clients for you instead of you launching them, as normally has to be done now with the current version of Flower. So to put a concrete example, we can go through a simple diagram of how you could use Flower now. So normally you need to start 2 processes. First, you have your server with your client manager, which is waiting for clients to connect. And on the other side, you have maybe a bash script that will launch multiple clients, let's say 10 clients. All these clients are alive at the same time, and they all connect to the server via the RPC connection. And because you have defined your experiment in a way that you have said what's the proportion of clients that will be sampled at every round, so the client manager will select M clients, and the global model is downloaded to those clients, and the clients do a fit function or a training function, and then after the training has finished, the model is sent back to the server where it gets aggregated, and then a new round starts. With the virtual client manager, it's a bit different. So you still launch a server, and instead of launching clients manually, you launch a virtual client manager. And this virtual client manager needs an additional piece of information, which is a config file, which could be a Topal file, indicating what are the resources that each of the clients will need. For example, 1 CPU and 2 gigabytes of VRAM, or different settings based on your experiment. And in this way, the virtual client manager is the one that connects to a new type of client manager on the server. The remote client manager will tell the virtual client manager, okay, for this experiment, I want 100 clients per round. So the virtual client manager will submit 100 clients to an scheduler. And from that scheduler, based on the hardware, basically based on the resources available on your system, more or less clients will be instantiated. And therefore, taken out from this queue. And then the process will be identical as before. And now in this case, two clients have been instantiated. They connect to the client manager and they do the feed round. And then once they have finished training, they send it back to the server. But in this case, unlike before, the round hasn't finished. We still need to complete all those 6 remaining clients. So what will happen is that those clients have finished their job, so they disappear. And then 2 more clients get instantiated and receive the global model, and they do the training. And this happens until we have completed the round. So effectively, what this means is that our round now can be subdivided into n sub-rounds. And we have more or less sub-rounds depending on the resources available in our system and the resources that we want to allocate for each individual client. So this idea of having sub-rounds effectively allow us to run experiments with as many clients per round as we really want. The only limiting factor would be how much time are we willing to wait for a round to end. For example, this will allow us to see how well my new strategy scales when I have thousands of clients in a given round. And what's the impact of privacy now that I can run rounds with many clients? Can I measure my privacy in those settings, like realistic settings with thousands or hundreds of thousands of clients? And what are the impacts of malicious actors? Now you are not limited to your typical 10 or 15 clients per round. You can measure this with thousands of clients per round. So all this apparently simple difference with respect to how we have been using Flower before, I think will allow us to do much more interesting research, and that will be probably closer to what eventually will become a real deployment, where normally we look at hundreds of thousands of devices. So yeah, sorry. And this scheduling can be implemented by hand based on existing schedulers, or you can implement your own. So far, we have been experimented with Ray, which is a library that allows distributed applications for machine learning or other topics. Here, in our case, for the virtual client manager, we are only using the core functionality of Ray, which in essence is launching jobs in a resource-aware fashion. And as well, this can be integrated with the existing workload manager like Slurm, which will allow you to scale to multiple node setups very easily. So before handing it to Tanner, I'll go through just 3 use cases to show how this can really change the way we have been working with federated learning, and in particular with Flower. So for example, in mind we have a setting where we want to train Feminist. So Feminist is an image classification dataset that has 3,500 clients. And normally you will see experiments using maybe 100 clients per round or 50 clients per round or less. What if now in my quad-core CPU laptop, I would like to run 200 clients per round? Normally, if you submit 200 clients straight away, you might end up having some compute and memory issues. But with a virtual client manager, because it is aware of what are the limitations and the resources needed for your clients, this will be a schedule. For example, in this case, it will be done 4 clients at a time. Therefore, we'll have 200 divided by 4 sub-rounds, which, as you can see here, is still a reasonable amount of time, only waiting for just under 3.5 minutes. What if we want to be a bit more ambitious and we want to have, for example, 1,000 partitions of a Cypher10 dataset, and we would like to use 100 clients, 100 GPU clients per round? How can I possibly achieve this without having, a very large amount of GPUs? So for this use case, we are thinking of, okay, we have REST 18. If your model size is no, if the partition of your dataset, because here we're talking about 1,000 partition, that means we have 50 images per client. We are enough. We're good to go with 2 gigabytes of VRAM and 2 CPU cores per client. If we want to use 100 clients per round, and if we were to have like a high-end GPU, we could allocate 16 clients simultaneously inside the same GPU, like in a V100. But if we don't have, that's not possible for us to get this kind of GPUs. You can, it doesn't matter. You can even use this in a lower end GPU. As long as you can fit one client, the virtual client manager will schedule everything for you. And in the case of having a V100, you can run these 100 GPU clients per round in just over a minute. What if we are even more ambitious and we have our on-premises cluster and we want to allow the virtual client manager to see and submit clients across multiple nodes? This can be achieved fairly easily with the scheduling mechanism we have been using, which is Ray. And this certainly will allow you to up to launching about 100,000 clients per round. Of course, there will be a schedule, but at least you can simulate and therefore understand what are the different machine learning dynamics happening in those kind of large scale experiments. And the key message here is that all this can be achieved with a single config file. So you have your server, virtual client manager, and the config file that describes the workload and specifically the resources needed for each client. So for example, if you want to run the same workload you might run for your Cypher 10 experiment, you can launch it in a laptop as well. It will be slower because you cannot allocate that many clients at a given point, but you can still perform the 1,000 clients per round if you want. So we think that the new virtual client manager will certainly allow you and everyone that is interested in federated learning to jump to the next level. I think then now Tanner will present a new type of client that will get rid of some of the problems that are associated with networking issues.
Yeah. Thanks, Javier. So the virtual client manager with Javier, which Javier presented, is one of the more concrete efforts we're taking for scaling basically the federated learning research. We're also experimenting with some different ideas where we are looking into reducing the memory footprint of for the cases where a developer is basically only working on a single machine and maybe has time but has memory limitations. So basically, you can run the laptop for 2 weeks, but you can't like put there 200 laptops. So in that case, you might be willing to trade off time for less resource requirements. With some limitations where you basically don't want to, where you're not interested in, for example, simulating compute limitations, which you can do with a virtual client manager, in those cases, you might be fine with using a sequential model kind of basically, which will compute each client sequentially. So now, can you go to the next? Thanks. So the idea with the in-memory client is basically giving you the advantage of having less memory consumption. Will utilize on a single machine and most of the resources, as most machine learning frameworks anyway utilize most of the machine resources. And the memory footprint will basically be limited to the Flower server and one client instead of n clients. The next one. Yeah, disadvantages are basically that we can't really scale it more than one machine, which we can do with the virtual client manager. We can't simulate networking, which is not good. If you want to simulate that, clients will be basically sequentially working or do the machine learning, and the environment basically is less real as you would be able to simulate with a virtual client manager. With regards to the implementation of this, on the next slide, in the current way we have in Flower, we have the federated learning loop and something which we call the client manager, which also Javier just presented as a remote client manager when combined with the virtual client manager. Then we have the internally the RPC server, which basically connects to all the clients and registers those clients in the client manager. The idea is what happens if we then have basically a single process where the clients directly register to the client manager. We are currently, as I said, exploring this idea, but we also see some issues with this approach. Maybe, can you go to the next? Thanks. The issues are basically, if you basically don't have this process barriers between the clients and the server and between the clients themselves, how do you ensure that, for example, a highly complex framework like TensorFlow or PyTorch, that they don't interfere with each other? We are still evaluating how much interference is there, but at least on the compute side, there is interference naturally. There is, for example, with things like the optimizer state and other internals of the machine learning frameworks, we see some issues which the researcher would have to handle. So there are still open questions if this is a feasible idea. Yeah, so this is one of the scalable approaches or ideas we are currently doing for making Flower more scalable for a single developer, as well as with its own machine, as well as research where you want to really scale to maybe hundreds of servers where you simulate thousands or millions of clients. On the final notes, the virtual client manager is coming to the main branch very soon. We are it's currently in a fork, and we're working on that. And then with regards to the in-memory clients, if somebody wants to have a look, it's currently in a pull request. Yeah, that's it. Thanks a lot.
Thank you both. That was really, I think it's a really great preview as to what Flower is going to soon be able to do that plugs a really important hole, I think, in current methodologies. So thank you for sharing it with us all. We have 3 questions I want to run past you. First question is it possible to send client updates as soon as some new local model update is available? So instead of the server asking for clients, the client would initiate the server-side collection. Any thoughts?
So this means, so I guess the question is related to to do the aggregation in an asynchronous way, probably. That's how I understand it, right? Instead of waiting for all the clients to finish, and therefore waiting for the, let's say, 50 clients to send back their model, start aggregating before that happens.
Yeah, I guess that's what it's getting at.
I guess that could happen, but probably I think that would link with the stragglers problem. I guess at some point you will have to maybe set a limit on how much you wait.
Right. Yeah. Okay. Well, anyway, we perhaps could move on to the next question as well. Question is, I was wondering if in your client manager, you do any kind of prefetching or data optimizations for speeding up the training process at scale.
We don't. I think the challenge I see there is that normally you want to keep all your data inside the clients, and therefore the data doesn't leave the clients. So ideally, we don't want any kind of pre-processing happening outside the clients. So yeah, so that's what I would say. Maybe there are ways to relax that. But if we want clients to behave as clients and therefore being like isolated beings, maybe that poses some limitation on how much we can speed it up.
I mean, maybe to also extend on that, what we have done previously in some cases, we basically, when we had a server or a machine running some clients, we prepared the machine so that at least locally on the machine, you have the data set at least downloaded, so that not each client starts fetching data from somewhere, so it can just read its specific partition from disk. So maybe that also answers part of the question.
Okay, sure. Final question that I see there is, are the clients sending the local update at the same time, or is it done in batches?
Currently, at least the way we have implemented the virtual client manager, it happens in no, they send it individually. The thing is that you need to, for example, if your sub round in the virtual client manager, your sub round is defined to be 5, for example, because you cannot fit more clients in your laptop or your computer. Then yes, individual clients can send their model back to the server as they finish, but then the server will be waiting for those 5 clients before the aggregation happens. So if there is one client that is very slow because maybe it has a lot of data or because the hardware is very limited, then that will be making the whole process waiting for that. So that highlights what the big problem with the stragglers.
Right, I see. Well, that is all the questions we have, and that's all the time we have. So it's a good alignment of resources, and yeah, so perfect. Thank you again, both, for that great talk. I think it's going to be really an important enabler for the community.